Thank you. First of all, I'd like to say thank you to organizers for this very nice workshop. So today we discuss a cavity QED model, implementation of a model in which we can play with different degrees of freedom of atoms. And this work is done in collaboration also with experimentalists. And so we really want to somehow show you a model which can be implemented. So we start with the implementation of this model. And we show you how we can, in this kind of model, realize interplay of the internal, meaning spin states of the atoms, and external degrees of freedom of atoms, meaning a momentum of these atoms. And we show how in this model, very nice non-equilibrium oscillatory phases can exist for a very long time, even though we don't have any kind of periodic driving in the system. We also discuss weaknesses of these non-equilibrium phases, how they can be observed in quite easy way. And we conclude with saying that the relaxation rate in this system is very tunable and can be fixed in different orders. So let's start with the Dicke model, which we have seen many times today. Today, it describes interaction of the cavity field, A, and a bunch of spins, which here are parameterized in the spins sigma. And we know that in these kind of models, there is phase transition. So when coupling eta is very small and smaller than critical, the observables like cavity field A and sigma plus sigma minus spins, they equal to 0, so we are at this point. But when we increase coupling above critical, two non-trivial solutions both for the cavity field and for the sigma spin appears, which correspond to the superradiant phase, stationary superradiant phase. And we know that if we perform quench protocol and we let system evolve according to this Dicke Lindblad master equation, the system finally will end up in this state, in the normal state, or in the superradiant phase state. So finally, state of the system is stationary. But today we discuss a case when different degrees of freedom of atoms can be described with this kind of Hamiltonian. So we have two subsystems, B and S here, and each of them can be described by the Dicke model. And what we will show is that in case when one of the coupling, for example, eta B is smaller than critical, and system is supposed to sit in this normal state, and another coupling is larger than critical, meaning we have symmetry broken in the system, actually some non-equilibrium process can be still observed. And these processes come from the fact that in this case, the superradiance in one subsystem acts as a drive on another subsystem, which induces very long-lived dynamical phases. We discuss a kind of from which observables we need to sit to be able to capture these non-stationary phases, and we discuss how we can observe these phases. So let us start with the way how the Dicke model can be implemented in a cavity QED. There are a few experiments, and we discuss both of them. So in the first case, as it was mentioned earlier today, there is a bunch of cold atoms trapped in a cavity. They are pumped with the transverse driving field with the strength eta s and the main frequency omega bar, which is out of resonance with the electronical transition. And again, in this case, what we can realize a scattering. So there is a two-photon process during which the atoms can change their momentum. So in this two-photon process, we start with the atoms in state 0. It interacts with the driving field and interacts with this cavity photon. And in the end, it can end up in the excited momentum state. And in this case, this model can be exactly mapped to the Dicke model. In this case, these pseudo-spins J, they are built from these different momentum states. And the level splitting in this case, it's equal to times recoil energy. And again, in this case, momentum external degrees of freedom can be addressed in the experiment. It's very useful to see how this phase transition, transition from the normal state to superradiance, looks like in this experiment. And to do so, it's useful to go back to the single body Hamiltonian. Here I omit a lot of terms and remained only the most important one, like kinetic energy and the lattice potential energy. And again, as it has been shown, so like when we are in a superradiant phase, when cavity field is non-zero, the atoms experience this lattice potential proportional to cosine kx. Cosine kz is just interference of the cavity field and the driving field. And atoms in equilibrium, they tend to see in minima of this lattice potential. What does it mean? Like if we look at the density profile of the atoms in the cavity, we can find out that along x and z axis there is modulation of the density. So this potential, cosine kx, cosine kz, it forms lattice. And along this lattice, we can observe this modulation of density. Less density, more density, and so on and so forth. Okay, there is another way how to realize a Dicke model in which a spin state of the atoms can be also addressed. In this case, a strong magnetic field is applied along z-axis, which induces a Zeeman splitting of levels with different magnetic numbers. And in this case, if we apply two driving fields, like one is red detuned and another one blue detuned, we can realize a transition in which ground motional state on one atomic level is coupled to excited motional state to another atomic level. The Dicke model in this case is also can be derived as a low energy limit, and these spins S, they are somehow a combination of the internal and external degrees of freedom of the spin and momentum. So it's like a pseudo spin built simultaneously from the two degrees of freedom. And again, like if you look on the single body Hamiltonians, here we see this additional term fx, which address like spin degrees of freedom of atoms. And in this case, the checkboard potential takes a more interesting form. So if you look and like if you consider only two level systems, like level 0 and 3, the density of the condensate, it also has spatial modulations. So here we have more density in the center, less density in between these cells. But also we can look on the another degrees of freedom, which is not only on the density of the condensate, but also the spin state. And we can find out that in one lattice side, the spin polarized to the left, in another lattice side, polarized to the right. In this case, it's called like a checkerboard potential, which is decorated with the spin degrees of freedom. So in this talk, what we are trying to do is we're trying to see which kind of dynamics we have when we combine these two driving schemes. So when we can simultaneously address internal and external degrees of freedom. We consider a model in which we have two cavity fields, basically which has combined to previous experiments. Yeah? In this case, it can be shown that minimal energy model can be written in terms of these four spins, which level 0 and 2, the ground momentum states on different atomic levels. And level 1 and 3 are excited momentum states on different atomic levels. So the minimal model can be read in this way. And at the first glance, it looks like that we have just two Dicke model, which acts on the different pseudo-spins and nothing interesting. But it's not the case, because all of the spins, J, they're built from the same atomic levels. And what it induces, like if you look on, you basically can generalize all possible transition in this matrix. And the very interesting thing comes from the fact that the different elements of this matrix, they do not commute. In general, there is this commutation relation, which in easy words can be transferred to the following picture. So this S spins, which are mixed degrees of freedom, and J spins, which are also momentum degrees of freedom, they do not commute. And in general, they are proportional to this third kind of spins, which are only internal spin, only atomic spin. And this non-commutativity actually can act as a driving on 1 degree of freedom if you have superradiance in another degrees of freedom. So to show this, we discuss dynamics of the system. To do so, we prepare atoms in a combination, a mixture of atoms on level 0 and 2. So we suppose that we do not have any kind of modulation of density in the system, but the spin state of atoms can be different. And we study dynamics by evolving system with different couplings eta S and eta B. And in this case, we can end up with the following phase diagram, which is, okay, we have, if we go along this axis and increase coupling eta S, this one we have a superradiance transition in cavity field AY and spin J. And if we go along this axis, we go transition from the normal state to superradiance state in cavity field AZ and SZ. But the curious thing appears if you look how this transition looks like again in terms of atoms, because now we have 2 degrees of freedom, internal spin and external spin, like density modulation and spin. So, for example, if we go along this axis, we again have the superradiance transition, and we have this modulation of density in the condensate, like smaller density or more density. But then, if we look on the dynamics of this internal spin, it's actually non-stationary. We can show out that in this case, the internal spin of the particles is processing with a frequency which is set of the parameters of both the subsystems. So, like the procession frequency is set not only by this omega s, but it also is controlled by the, for example, number of photons in the systems that we have. The more interesting transition happens when we go along this axis. Because here we have superradiance in SX spins, which is not internal spin, neither external, it's some mixture. And in this case, this like mixture, superradiance in this mixed state, acts as a driving for both density modulation and then spin degrees of freedom. So here we plot as like some sketch of the density of this atomic degrees of freedom with time, and we can see that the density modulation is changing in time. So here we have all like, for example, here we can recognize that all particles are polarized to the left, and also we have one form of the density modulation, like more particles here, less particles here. But then after a quarter of the period, we have like mirrored picture. All particles are polarized to the right, and we have smaller density in the first side, more density in the second one. And also, like we can show that if we are in this region when both couplings are greater than critical, there are some procession of the internal degrees of freedom can be observed for a very long time. Okay, so it's what happened to the spins. But the similar dynamics can be reconstructed if we look on the dynamics of the cavity field. Because in this model, we are working in a limit when the cavity detuning and also cavity decay kappa, they are much larger than the rest of the energy parameters, and these photons can be eliminated. And what does it mean? That at times of order 1 over kappa, the spins, the photons, they are actually proportional to the spins. So if we know dynamics of the spin, we also it also means that this cavity field is also evolves. So to show this, let us consider the following case when we prepare system in the normal states, then we drive system to the superradiant phase, let it equilibrate, and then we increase second coupling and see how dynamics in this case looks like in terms of the cavity field. So here we are. Here we show a protocol. So yeah, as we saw, we first increase coupling eta s and then increase coupling eta b. And at this point, we realize that superradiant state in the cavity mode, in the cavity field AY, and the number of photons in this field becomes non-zero. And it corresponds to the case when for the checkerboard lattice we obtain some fixed density modulation. But again, this internal spin can process, as it's shown here. Then we start to increase second coupling. And in this case, like we start with this procession. But what's going next that when we start to increase second coupling, we also induce some more interesting modulation of density. So now these particles can fly between all of these 4 levels. And also the orbits along which spin degrees of freedom is evolving, it also becomes different. And these dynamics take place up to the time when basically all particles can fly from, for example, levels 2 and 3 to levels 0 and 1. So when all dynamics can be somehow localized up to 2-level case. In this case, it happens at this point. And finally, on a very long time, we can observe that the checkerboard lattice gets some final profile, density modulation, and also all spins polarized more or less to the right. So here there is this very interesting region in which we can observe this persistent oscillation of the number of photons in the cavity mode AZ. And let us look closer at the dynamics along this time. So here we can, like if we look closer, we see this persistent oscillation. So the cavity number of photons in the cavity is that it oscillates between 0 and non-zero value. And also every time when it is takes 0 value, we have jump of the phase of the cavity field equal by pi. It means just, if you look on the dynamic chest by observable AZ, it means that it periodically changes in sign. So it's really like oscillates between the two different quarters. The good thing is that the duration of this phase in which the system is definitely out of equilibrium, it can be tuned by varying different parameters of the system, for example, coupling, and also by changing the initial state by putting more or less particles on level 0. It also can be varied with different order parameters like this level splitting, but in this case, dependence is more complicated. Okay, finally, let me try to convince you that we really have something like a pumping, but plotting the change of the energy in the system with time. To do so in a very simplified manner, we just solve Liebman-Master equation for the Hamiltonian. Yeah, so like in this case, we can appreciate what happens to the energy of the system with time, and we can really show that, okay, this cavity photons, they couples to some pairs of levels. For example, for level 0, 1, 2, 3, 0, 3, 1, 2. And we can see that the contribution from some of these levels, we effectively pump the energy to the system. And from the like these levels, for example, we reduce energy of the system. And so like system acting as a self-pump for itself. And in this, again, by varying the parameters of the system, we can really slow down relaxation of the system up to, okay, here I was very happy 1 week ago and wrote 1 second, but after yesterday when I heard like 8 hours, I'm a bit okay. Not so happy anymore, but yeah. Okay, so finally, let me shortly advertise our work in which we have studied, another work in which we actually study how the, by merging some ideas from the solid-state physics by considering some physics in the magnet-metal heterostructure, and yeah, actually here what we have done, we considered a minimal model which can simultaneously capture the cavity QED system and magnet-metal heterostructure. We show which are ingredients we should add to both systems to end up with the same effective model, and we show that which interesting hybrid phases we can derive in this case and observe in this case. So yeah, so today we discussed that by inducing the interplay between internal and external degrees of freedom, we can really induce and observe very nice non-equilibrium dynamics for a very long time. Thank you.